Hi, it's time for another math easy solution. To discuss further into calculus with parametric curves, and now look at arc length and go over the proof part 3, which is I'm going to revisit it. I've actually went over this in my earlier video, and I realized that the derivation I went over was wrong. And basically recap on what I've done in that video, and I've since made it private. Basically, if you go look at arc length, so let's go over. So recall from part 2 that I showed that the arc length for a parametric curve is given by the following theorem, and here it is. If a curve C is described by the parametric equations x equals f of t, y equals g of t, and t is between alpha and beta, where f prime and g prime are continuous on the interval from alpha to beta, and c is traversed exactly once as t increases from alpha to beta, then the length of c is given by this arc length formula. L equals 2 integral from alpha to beta of square root dx over dt squared plus dy over dt squared, and then multiplied by dt there. This formula was derived by assuming that ti star equals to ti double star in the following equation that I went over in part 2, so make sure to watch that. And I'll put that in the video description below, where L, the arc length, equals to the limit of n approaches infinity of the summation from I equals 1 to n of square root, and then we have f prime ti star squared, and then plus g prime ti double star squared delta t. The problem with this is that this sum is not exactly a Riemann sum because ti star does not always equal to ti double star, as in here. But in part 2 I just assumed that they're the same, so we could use the Riemann sum and write that as an integral. Again, you can learn more about Riemann sums and integrals in my earlier video. I'll put that in the description below. But with the problem I did when I made the part 3 video originally was that, well, I squared that summation. I looked at it, and basically what I did was, let's see what happens when ti star is not equal to ti double star. So what I did, I squared the overall summation. But then the problem I made is I stated that it was equal to while squaring the inside sum and this delta t as well. But this is wrong. You can't just do that, and I'll show you why. And then from there I went and got 4 Riemann sums. Again, I'm going to put a giant X. You can't just do all this stuff. And then we got this 4 Riemann sums over here, and then eventually got integrals. And then I combined all of these integrals, and having these random squares like that is all wrong. And then I also square rooted this, which is also wrong, like that. Yeah, so I square rooted this this giant integral because right here you have a square root, and then I square root the inside the integrand as well. So this is in fact wrong. So I'm going to do an update. The proof above is wrong. And yeah, basically, there was no proof in my calculus book, so I went over it quickly, and then I just went over these steps, and then for some reason I got the correct answer, which is why I made the video. But then I realized, well, you can't just do this. Regardless whether it was correct or not, the final answer, the steps taken were all wrong. So I've since made the video private, and here is the link to it. I'll just click here to show it. Yeah, and here's the video I made last week as well, and then you could see the notes, and it's the exact same thing, yeah, that I covered just now. Yeah, and you could see here it's that same thing I just went over, and I just wanted to show you the notes to it, and this method is just all wrong, all the steps that I took. So I put a giant false label there and made it private, just so I wrote the falses for reference for myself. But anyway, so I've since made the video private, and the reason for this is that what we do to the integral or summation does not mean we do the same to the integrand or function being summed as when above. For example, squaring the integral or summation does not mean we square the integral or inside the summation, etc. So consider the following examples. For example, let's say we had I is equal to, or instead of I, let's call this S. So S for summation is equal to the summation I equals to 1 up to 3 of, well, I. This one here is simply, this is just 1. So when I is 1, we put 1, plus when I is 2, we plus 2, and then 3 all the way up to 3. So is this 1 plus 2 plus 3? This is 1 plus 2 is 3, plus 3 is 6. Like that. So S is 6. But then if we square this, like that, s squared, this equals to, well, the square of the summation, I equals 1 up to 3 of I, like that, and we know this is equal to 6, so that equals to 6 squared, which equals to 36, like that. Yeah, so the 6 goes into there, and we get 36. Now the problem here is if we were to, well, instead of doing this and then sum the inside, so instead if we had something like where we square this and it squares inside the function being summed, which is in this case I, what we get is, well, this is I is 1 up to 3 of I squared. So here we're squaring it. Now what we get is, well, when I is 1, we get 1 squared is just 1 plus 2 squared plus 3 squared. This is going to be, well, this is 4. And yeah, so that's 4. This one is 9. So we get 1 plus 4 plus 9. 1 squared is just 1. So now we get 1 plus 4 is 5 plus 9. That is just 14. So this is not equal to this 36 right there. So as you can see, we can't just do this right here. So in other words, summation of I equals 1 up to 3I squared, I all squared, is not equal to the summation of I is equal to 1 up to 3I squared. So we can't just do this. So this is not equal to it. And that's what I did over here is what I did over here is, here I did this summation in my earlier video, and then I put it inside integrand, inside the summation. So you can't do that. So the steps were wrong, even though I eventually got the final result was the same. But regardless, the steps were wrong. Now similarly, I'll just write that. Similarly, if we did it for an integral, we can't do the same. We can't do that same method for an integral as well. So similarly. Oops, I think I spelled wrong, so there's no I over there. Similarly, if we had, let's say instead now we have I for integral, I is equal to the integral from 0 to 1 of now we have this, x. I'll just do a simple function x dx. This is equal to, if we were to integrate this, integral of x is just, well, x squared over 2. And then this is the integral is from, well, 0 to 1. So we evaluate it, put the 1 in, we get 1 over 2 minus 0 over 2 is a 0. So we get 1 over 2. Now if we square this, I squared is equal to integral from 0 to 1 of x dx all squared. This equals to, we'll just plug in the 1 over 2 inside. We get 1 over 2 squared is equal to, well, 1 over 4, like that. But now what we have is, well, if we had this, if, oh, it's not a 5, if, and I'll put this if and I'll square that like that. If we could put this inside the integrand, the problem here is what we get is, well, if we had a 0, 1, x squared, and then we have this dx squared like that, well, we can't even, this one is a problem in itself as well. So if we were to do this and this becomes x squared, separate this into 2, dx times it by 0 to 1, 0 to 1 dx, and I'm going to put another marker here. We can't do this either. Just to make it 100% clear, we can't just necessarily do this. And I'm including this just for reference to show you if we could, we'll still get the wrong answer. So if we were to do this and separate it like I did above, what we have is now, because we have this dx squared, which is a problem of itself, so we can't have that in an integral, which I was dealing with over here, etc. So these are all wrong. I just wanted to fully clarify that. And dx squared is more for 3D integrals or double integrals, which I'll get over in later videos. So if we had this, and then we could integrate this, if we could do this all, this is going to be x squared, that is x cubed over 3, from 0 to 1, times it by, now this is just 1, it can be seen as a function, it's just 1, 0 to 1 integral of 1, that's, well, the integral of 1 is just x, it's the constant, so integral from 0 to 1, like that. So now we evaluate both of these, this equals 2, well, this is 1 over 3, so I'll put this over here actually. this is 1 over 3. So we put the 1 over 3 minus 0 over 3 is a 0. Then here we have 1 minus 0. That's just 1. So we get 1 over 3, which this one is not equal to this right here. So this is not equal to 1 over 4. Yeah, so thus what we have is, well, the integral from 0 to 1 of x dx. Well, when we square this, this is not equal to the integral from 0 to 1 x squared, or just put this inside here, x dx squared. Yeah, so this is not equal to it, or not necessarily equal to it. And in fact, you can't even have this. This is a problem of itself. This is when you square these. I just put that in. This one, I just took the square and moved it outside like that. So we can't just do this. And I'll put an x like that as well on it. So anyways, and now to get back to what we actually can mathematically do as well, to show that the above sum, and that's the Riemann sum, is actually a Riemann sum, or in fact correspond to Riemann sum. That's this one over here. I wrote it down. I'll just go all the way up here to show that this. So the whole point of this part 3, when I did before, was to show that this, we could write it as a Riemann sum eventually, or 4 Riemann sums. So this one, when we take this into this summation, and I'll just scroll all the way back down, so I'll show you that this does in fact correspond to a Riemann sum, and it's actually pretty straightforward. So when we look at this this giant summation, so what we have to do is recall from part 2. So recall from part 2 that Ti star and Ti double star are within, or are inside, are in the interval from Ti minus 1 to Ti, like that. And now if you were to graph these two, so if you graph it like this, this is from T, and here we'll have X and Y graphed on the same axis. So for example, if you had X that looks something like this, and I'll go from here to here, I'll just do a giant interval for just illustrative purposes. So if this is Ti minus 1, remember the polygonal approximation, this is Ti, and this is, we'll say this is our X function, and now let's say we have a Y function like this. It could be somewhere like that, up to here, and this is across there, and this one is our Y, like that. And that's crossing at this point here, and then basically, yeah, and basically the Ti star and Ti double star were found by the mean value theorem. So recall from that, and that's basically finding where the derivative is the same along from this average slope like that is the same across here. So this one was for the Y, that was our Ti double star. And for the X one, that was the, so basically that was Ti star, and that's when you look at this line across from here to here, we have this slope across, which is identical to this one, and that's at this point. This is by, again, mean value theorem, so make sure to watch that video. This is Ti star. So now I'll put this reference like that. This and this by mean value theorem. This is again from the earlier video on part 2, so make sure to watch that one. Pretty cool stuff. And also want to point out that this distance Ti to Ti minus 1 to Ti is, well, our delta T, which was, we impose that is the same for all values of Ti, like that. And now, as well as n is approaching infinity, so this means we have infinite amount of polygons or intervals in this summation, so we're going to be summing infinite amount. And recall, when that happens, the only way that can happen is, well, this interval delta t. So as n approaches infinity, then delta t, well, this approaches, well, dt, as in the integral, which is, well, infinitely small. So it's, in other words, it's approaching 0 but never actually reaches it. So infinitely small. Yeah, here, just fix that spelling mistakes. Infinitely, there's an E there. So infinitely small. So in other words, this is, well, approaching 0, but never actually reaches it. Yeah, thus this means that these two are getting, well, infinitely closer and closer together. Just ti minus 1 at ti, and likewise the ti star and ti double star, all of them start approaching smaller and smaller, approaching the 0 mark. So in other words, we have thus ti minus 1, ti star, ti double star, and ti all approach the same value, or approach the same value, because the difference is very, very small. It's the same value, and we'll call that just t. And thus the summation behaves in the exact same way as an exact Riemann sum, as basically n approaches infinity, because all these values are approaching the same value t, and thus we get the definite integral from the Riemann sum method. We get L is equal to the integral from alpha to beta of square root. Now we have this f prime of t squared plus g prime of t. So the ti stars, ti double stars just become the t like that squared, and then the dt, where that's where the dt is approaching infinitely small, and we get this integral. And now this one here, we could write this in Leibniz notation. It's the same thing as writing L is equal to integral from alpha to beta of square root dx over dt squared plus dy over dt squared, and this is all square rooted, and then we put a dt at the end there, like that. And we could just I'm going to circle all this. And there is our proof that even though the ti and ti double star weren't the same, it's still technically the same. It will approaches the same as n approaches infinity. So anyways, that's all for today. If you learned from this video, and also what you shouldn't do, what you can't do in terms of integrals and summations, and also wanted to clarify my mistake in my earlier video. So sorry about that. Anyways, thanks for watching, and like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.